are comparing linear, exponential, and quadratic functions. And there's going to be 3 different ways that we can compare them. So let's go ahead and break our table, or make a table. So that we have linear, exponential, and quadratic. Okay, so linear, let's go ahead and look at the graph. So linear graphs, they are straight. So they could either be increasing, they could be decreasing, they could have a slope of 0, but all of them, so it's either one or the other, all of them are straight. Exponential graphs, there's definitely curves to them, but the difference between exponential and quadratic graphs is that a quadratic is symmetrical. So it looks like a U going up or going down. Exponential has a curve, but it's not symmetrical. So it's either this, where it's exponential growth, or it tapers out, so it could be exponential decay. So either one of those is an option. Give me just a second, my pen died. Okay, so it could taper out like that, and then it could be exponential growth or exponential decay. So the difference is with linear, it is straight all the time, every time. With exponential, we have a steep curve, and it's not symmetrical. And quadratic, we do have a symmetrical graph. And they also have this thing called a vertex and the axis of symmetry, which I've been shortening to AOS. Okay. If we look at their equations, then it looks a little bit different. So this one we have y equals mx plus b. That's our slope-intercept form. Okay, the m is the slope or the rate of change. Okay, as x is changing, we're wondering how fast is y changing. For b, this is our y-intercept, or our starting points. Okay, when x is 0, or sometimes when time is 0, if we're doing it with time. For exponential, we use the equation y equals a b to the x. So the important thing here is this is now our y-intercept, okay? It doesn't have the variable, just like this b doesn't have the variable. And this one is not necessarily our slope, but it is our common ratio. It's the common thing that is being multiplied each time. Then we have y equals ax squared plus bx plus c. Okay. So we have a is going to tell us whether or not we are stretching, shrinking, or reflecting. B of x we will get to, but that kind of tells us where the vertex moves and where the axis of symmetry is. And then C, this is going to be our y-intercept. And again, the y-intercept is always on its own without a variable. Okay? All right, so let's look at the 3 and see how they are different. They all have an x and they all have a y. But how are they different? So the y-intercept, or sorry, the linear ones, they have an exponent that is just 1. So the exponent of x is 1. The exponential kind of is given away in the title, so the exponent is the variable. And then for the quadratic, what sets this apart is that it has an exponent of 2. zoom in, we have an exponent of 2. Okay. Now, let's look at an example of each of these and see how do they compare when we're given a table of values. So let's do the example y equals 2x plus 5. And if we make a table of values, x and y, we can go from -2 to -1, 0, 1, and 2. So my x's, those are increasing by adding 1 repeatedly. My y values, I can go ahead and start and say that, well, when it's 0, then this is 5. Okay. And then I could plug in 1 and say, okay, well, 2 times 1 is 2, plus 5 is 7. We could plug in 2, and we could say, okay, 2 times 2 is 4, plus 5 is 9. We can also take into account that we have a slope of 2, which means I'm increasing by 2 over 1. So if I'm increasing by 2 over 1, then I can say that this would be 3 and this would be 1. Okay, so we are adding consistently from one to the next. If we look at an example over here of y equals 4 times 3 raised to the x, and I use those same values, -2, -1, 0, 1, and 2, my y-intercept is going to be the value without x, so it's going to be 4. And then I'm multiplying by 3, so I could go ahead and plug in 1. Oops. Okay, so 3 to the first power is 3 times 4 is 12. And then if I do it again, then I get 3 to the second power is 9. So 4 times 9 is now 36. So my common pattern up top is still +1. That didn't change. But to go from one to the next, I am multiplying by 3. So we could go backwards and say, okay, well, what multiplied by 3 is 4? 4/3. Or I could just, instead of multiplying by 3 to go the other way, I could divide by 3, which would make that 4/9. So the common thing here is that we are multiplying consistently. Now let's look at a quadratic example. So we have y equals x squared plus 2x minus 1. We have x, and we have y, -2, -1, 0, 1, and 2. So again, my y-intercept, we can start with -1. And so in order to actually solve for these, we need to plug in. So if I plug in 1 for all of these, 1 squared plus 2 times 1 minus 1. So that gives us 1 plus 2 minus 1, and that's going to give us 2. If I change that, and I'm now plugging in 2, then 2 squared is now 4. 2 times 4 is, 2 times 2 is 4, and that gives us a 7. Okay, I can change those values again. Let's do -2. So -2 squared is 4. Minus 4 this time, minus 1. Well, 4 minus 4 is 0, so that's going to give us -1. And we've got 1 left, so let's plug in -1. So -1 squared is 1. 2 times -1 is -2 minus 1, and that gives us -2. Now, because this is starting to reflect, I can say that this is going to be my vertex right here. So then we have that gets created by, so we're adding one here. To go here, we're actually subtracting 1, and then we're adding 1, and then we're adding 3, and then we're adding 5. So there's no common thing here. But what if we go from here to here? Then we're adding 2, and we're adding 2, and we're adding 2. So see how these are all in common? Okay. This is called your first order of differences. And that second one is your second order of differences. So notice how the second order of differences, it happens to be a 2, but it's not always going to be a 2, but what matters is it will always match. And this 2 right here, the second, comes from the exponent up here. So we have a commonality between this second order and this exponent. And that makes sense because over here, it was the first order differences. That was our first order. And there's a 1 on this exponent. Now, later on, you'll see what happens if you have y equals x cubed. You're going to have to go all the way to the third order to get them to be the same. But when you're given a table of values, first see if you're adding consistently or if you're multiplying consistently. And if you're not doing any of those, then chances are you're going to have to go to the second order and see if that's consistent. That's it for today. Let me know if you have any questions.